Hello, my name is Gustavo Moreira. I'm a second-year PhD student at the University of Illinois, Chicago. Welcome to our presentation entitled The Urban Toolkit, a grammar-based framework for urban visual analytics. I would like to start this presentation with a fundamental question that drove and has been driving the work we do. How can we increase accessibility to urban visual analytics? The goal of the first half of my presentation is to clarify why such a question is relevant and worth tackling in the first place. The current stage of urban analytics poses a number of challenges we are interested in tackling. First of all, lack of flexibility. Tools and techniques are not translatable to other domains or regions. Lack of extensibility, it's very hard to add new functionalities. Lack of reproducibility, results are rarely reproducible. Lack of scalability, analyses are rarely interactive, which means that they limit the hypothesis and the exploratory process. Lack of accessibility, tools and techniques are often difficult for different types of stakeholders to use. And the development effort. So projects require expressive coding time and are often the result of disconnected efforts. There are several notable research efforts that tackle some of the previous challenges. To exemplify, some works propose systems and techniques to support the exploration of taxi trips data, support data-driven approaches to urban development, analyze the visibility of candidate buildings, or even study the impact of shadows in different development scenarios. All these solutions make valuable contributions to the analysis of urban data, but problems such as the substantial development effort required and lack of reproducibility still need to be addressed. On the other hand, popular GIS tools, namely ArcGIS and QGIS, provide highly scalable solutions at the expense of flexibility and accessibility, given its overwhelming number of operations and toolboxes. Another important aspect of these tools is that they often are closed software with some of their resources requiring payment. Before I present the solution we are proposing, it's important for us to understand where the complexity of the problem lies. First of all, cities are a vast repository of different types of data, including time series collected from sensors, data that have spatial and temporal components to it, such as text strips, 3D data, such as the buildings that are usually represented as meshes, and images, such as the images collected by private and crowdsourcing initiatives. Additionally, the diversity is also present on the user side. Different types of users with different backgrounds are interested in the data. All of that is made even more complex if we add the diversity of problems. Users might want to use the data to solve a variety of problems related, for instance, to urban accessibility, air and noise pollution, sunlight access, impact of climate change, and so on. Acknowledging all the presented challenges, our goals are: support the analysis of layered 3D or 2D urban data from multiple sources and formats, allow the use of different physical and thematic layers across scales and time, facilitate analysis across different domains, and do all of that while preserving flexibility, reproducibility, and extensibility. All of that brings us to our initial question. How can we increase accessibility to urban visual analytics? As an answer, we propose the Urban Toolkit. Our grammar-based approach paired with a toolkit capable of loading, processing, and visualizing complex data allows us to build a powerful visual analytics system for urban data. Let's start by understanding how our grammar works. Our high-level visualization grammar supports three of our main design goals: reproducibility, flexibility, and extensibility. When we take a look at our grammar, the basic components are the views, the camera position and direction, the data layers, and the plots. Talking a little bit more about the views and layers, the views contain map, knots, and plots. The knots is how we call the data layers loaded into the system. The data layers, as I mentioned, can take up the form of thematic and physical layers. The thematic layers are abstract data that come from simulations or sensing. And the physical layers represent the physical formats of the city, so the buildings, the parks, the roads, and so on. Layers can be linked together, with spatial operations to form the knots. Depending how thematic and physical layers are linked, we might have different results, as you can see on the right. Our analytical capabilities mainly lie on the plots. We leverage the power and flexibility of another high-level grammar called VIS to build them. These plots can be juxtaposed, lying on the screen, or plotted on top of the buildings or following their footprint. We also extended VIS to link its interactions to the spatial view. Given that we have a grammar specification, the toolkit will take care of shaping the entire visual analytics system around the grammar. To understand better how that happens, let's take a look at the architecture. The architecture is divided between front-end and back-end. We're going to start with the back-end. The back-end is responsible for loading and converting the data provided by the user from a variety of well-known formats so it can be manipulated by UTK. Also, data can be downloaded from OpenStreetMap or obtained through shadow simulation. The output format of those layers depend on their types. So physical layers can be polygons, triangle meshes, network data, and grids. The thematic layers are tuples of coordinates and values. The front-end module, on the other hand, is responsible for creating the visuals from the data layers and the grammar specification. The result can be something like the right picture. On the right picture, we have text strips aggregated by zip code and a parallel coordinates showing other dimensions of the data. The highlight in blue is due to the interaction link between the map and the plot. But one of the biggest challenges with a tool like UTK is conducting an effective evaluation. To do that, we defined a mixed approach by having 4 case studies that were motivated by real-world problems, like analyzing sunlight access during different seasons of the year, and also collecting feedback from domain experts through semi-structured interviews. Due to our time constraint, I will only discuss one of the use cases. Please refer to the paper for detailed descriptions of the other parts of the evaluation. Our use case takes place in Boston. We wanted to understand how a historic landmark such as the Trinity Church, a 146-year-old building, can be impacted by the new development of the John Hancock Tower, a 60-story skyscraper. That is because one of the most important causes of building deterioration is the shadow cast by neighboring buildings. We then used UTK to accumulate shadow casts during summer and winter and created a what-if scenario. So I'll quickly walk you through how you can use UTK to tackle that scenario. We can start with the backend and use the Jupyter API to fetch the data. So we have fetched the buildings for Boston and using our shadow simulation to simulate the shadow casted by winter and summer. Then we can define the grammar using the knots to build the what-if scenarios between comparing when the building is there and without the building. Now, having the data files and also the grammar, we can input those to UrbanTK and have a final visualization. So as you can see, we are comparing winter and summer and also the current scenario and the difference between scenarios. And we can see that indeed, the Trinity Church is impacted by the tower and also the public garden on the back. But even though we believe UTK is a powerful tool, some limitations need to be highlighted regarding the current state of the system. Operations can be computationally expensive for large-scale data. We have limited scalability of resolution due to the spatial operations we perform. And the use of temporal data requires verbal specifications on the grammar. And finally, we only have support to shadow simulations. Finally, the Urban Toolkit is a tool for design, authoring, deployment, and sharing of urban visual analytics applications. We hope to help with the popularization of urban analytics and to pave the way for a more robust ecosystem of open tools. Thank you very much for your attention, and thank you for the interest in our project.